All right, guys, we are going into, stop doing that. Okay, all right. You guys couldn't see it, I don't think anyways, but it doesn't matter. Anyways, here we go. So, welcome to video number 2. Today we are doing graphing exponential functions. I wanted to put functions on here, but it took up too much space. So it just says graphing exponentials. You guys get the idea. It's a function. We're doing graphing exponential functions. It's not too bad. We are basically just using transformation rules, and yeah. Okay, here we go. All right, everything came back. Good for us. Also, hold on, I'm gonna pause. You guys aren't gonna notice anything except I'm gonna be wearing something different when I come back because I'm really cold. Okay, I'm back. We're recording now. Sorry, I was really cold. All right. Yeah, that's okay. It doesn't matter. All right, here we go. Minimize. There we go. Okay. So notes, exponential graphing. All right, so first we're going to review some basic transformation rules just to make sure you guys we're all on the same page. It has been a long time since we've graphed with transformation rules, so I forgive you if you forgot all of this. All right, so really fast, you have two types of transformations. You have vertical and you have horizontal. All right, so the first thing you have to do is identify which one's vertical, which one's horizontal. Essentially, the rule is vertical transformations happen outside of the function, horizontal transformations happen inside the function. So both A and D are going to be your vertical transformations because they're outside the function. And that leaves, what the heck colors are these? C and B as our two horizontal transformations. All right, so that's step number 1, figuring out what's vertical, what's horizontal. Vertical is going to affect your y values, whereas horizontal is going to affect your x values. All right, so running through let's pick different colors here. All right, so let's run through our vertical transformations. First, these are the ones that are a little bit easier. People tend to like the vertical ones better because they are a bit more straightforward. All right, so our vertical ones. So first, let's talk about A. All right, A itself, the number out front, this is going to be a dilation. So this is your vertical dilation. That's a stretch, right? Dilation. If A is greater than 1, you're looking at a stretch. It's going to make your function taller. If A is a number between 0 and 1, so A is a fraction, this is going to be a shrink. It's going to make your graph shorter. All right. If you have a negative A, all right, this is a reflection. All right, there we go. All right, so negative A is a reflection. All right, upside down. All right, so it takes your graph and it reflects it upside down. All right, it is reflecting it over that x-axis. All right, so it's just bloop, reflect upside down. All right, the last one we have is D. All right, this is your translation or slide up and down. So translation. All right, if you have a plus D, this is moving your graph up. If you have a minus D, this is moving your graph down. Okay, so that is your, those are your vertical transformations. Very straightforward, right? The number out front is a vertical dilation. If it's greater than 1, it's stretching your y values. It's literally taking the y values for your coordinate points and multiplying them by whatever the a value is, right? So if it's a bigger than 1, it's a stretch. If you're multiplying your y values by a number that's between 0 and 1, it's a shrink. It's going to take your y values and make them smaller. All right. If it's a negative a, that's a reflection, so that's going to flip your graph upside down. And then looking at the end, your d value is just going to translate or shift all of your points either up if d is a plus d or down if you have a minus d. All right, so moving onwards, now we're going to take a look at our horizontal ones. These are the ones that are a little bit weird, but we just deal with it. Okay, so horizontal. All right, so let's first talk about the B. All right, so B is your horizontal stretch. or horizontal dilation. I don't care if you say stretch or dilation, doesn't matter to me. Just need to specify if it's horizontal or vertical. All right, so B, which is the number that you're multiplying or dividing by on the inside, is going to be your horizontal dilation. Now, I want you to pay close attention to how I have this written. Right now, I have B written underneath the x minus c bit, which means what you really have right now in my picture is 1 over B. So B, this B thing is a fraction. Now, if B itself, written how I have it in the picture, is a number greater than 1, all right, so if B is greater than 1, meaning what you actually have is 1 over a number greater than 1, so a fraction, right? Like 1, if B is 2, you have 1/2. If B is 3, you have 1/3, right? So B is greater than 1, written like this, meaning it's underneath, then you kind of are dealing with you're multiplying by technically a fraction, but it looks like B itself is a whole number. All right, but if B is greater than 1, this is going to stretch your function horizontally. All right, but remember, B isn't really greater than 1. What you're doing is you're multiplying by a fraction. But you guys get that, right? Maybe I'll write on the side so you guys will understand more. Remember when we did like trig functions, right? I'm just like rewriting the inside. I always told you guys, pull that B value out. And so then what you have on the inside is something like this, right? So that you could see your period and your phase shift better. This is kind of what I'm talking about. So if that 1 over B is actually like a fraction, where meaning like B is greater than 1, then this is going to be a stretch, okay? So B greater than 1, this is a stretch. And just like a vertical dilation, that A value is what we're multiplying our Y values by, this one we're multiplying our X values because it's horizontal, so it's a stretch. We're stretching, we're taking our X values, we're multiplying them by whatever B is, right? So it's a stretch by B. All right, if B is a fraction, all right, that's going to be a shrink. Now, if B is a fraction, that means you have something like 1 over 1/2, right? 1 over 1/2 or 1 over B, which really means that the number that you're multiplying by is a whole number, okay? So it's going to look like a whole number in the problem, right? So for instance, right, if it was a whole number, you would end up with something like this, right? Simplifies to a whole number, but really that's not this actually multiplying by a whole number. What you're actually doing is you're shrinking by B. You're multiplying, you're essentially like dividing it by B, right? So this is actually going to be a shrink. Okay, so it's kind of like the opposite of what you think. All right, so if you're writing it like I have actually like typed up, right, B being a whole number, you're like, oh, okay, it's a whole number, so it's a stretch. That makes sense. But if you actually think about it, if you're dividing by a whole number, it means you're multiplying by a fraction, but it actually is stretching your function, which seems really counterintuitive, but that's how it works. All right, if B was actually a whole number, right, so you would see it kind of on the top of the fraction, then you're actually shrinking by whatever B is. It's wild. It's kind of, like I said, it's the opposite. All right, so we've talked about that. Negative B, all right? So if B ends up being a negative number, this is going to be a reflection. Reflection, right? And it's backwards, right? So we're taking our function and we're reflecting it backwards, right? We're going like this, right? It's a reflection over your y-axis. Right, we can jot down there. We want to see more fancy than just saying backwards. We can say over the y-axis. Whereas this one is a reflection. We said upside down, right? This is, we can say a reflection over the x-axis, right? Because we're fancy like that. All right, nothing really to that. It just flips it backwards. All right, last but not least is the C. So what I kind of more like to do when I'm looking at the C is instead of just looking at C itself, right, let's take it where we're looking at the whole thing right here. All right, so if you have minus c, all right, so here we go, writing it down at the bottom. I just got to find the blue. There it goes. All right, so c is your translation, left, right. Okay, so hold on, let's move that way. All right, so c is your translation. If you have, so if what you have in that green box is a plus c, so it's x plus c, you are actually moving left by c. All right, and if what you have inside that green box is minus c, like we have right now, x minus c, you are actually moving to the right by c. So again, same kind of ideology with the dilation piece. It's the opposite of what you think, right? So normally you would think plus, you would be moving to the right, but actually it's, since the equation itself has a minus, in order to get to a plus, the c value you plugged in actually had to be negative, right? So if you get x plus c, since the equation is x minus c to begin with, then what that means is you had to plug in like a negative c value for it to be a minus and negative to make a positive, and that's why a plus c moves us left. Whereas a minus c, it means the c value is positive, so it just stayed x minus c, which means since it's a positive c value, you're moving to the right. But it shows up as looking like a minus c, which looks like a negative. Okay, so the general rules. Now, if you've been sitting here the whole time wondering what in the world the F is out front, F stands for function. All right, so that's where whatever function you're dealing with goes. So since this unit, we're doing exponential functions, our function, writing it like an exponential, would actually look something like this. All right, so I just gave you guys the generic one to begin with. Now for ours, y equals a times b to the power of x minus c over the b in the equation. All right, our b right here is b for base number, and the b up here is your b for your transformations. I know it's weird, but they're different b's. They're not the same. All right, we would say this is b for base number. All right, plus d on the outside. All right, so that's what this one looks like. So you've got your a out front, you have your function, which is your base number, and then your exponent is the function-y piece. So anything in the exponent, those are your horizontal transformations, and then anything out of the exponent, so your a and your d are your vertical transformations. Okay, good stuff. Let's take a look at the parent function really quick. So I'm gonna go pretty fast. You guys have already seen the parent functions before in Algebra 2, so we're just doing like a recap of this. All right, the basic parent function for an exponential is a base number of 2 and to the power of x. All right, why 2? Well, normally you would say you start with 1 because it's the smallest number, but you can't have a base number of 1 because then it would just be a flat line. So we can't have a base number of 1. So then the next smallest number is 2. All right, so y equals 2 to the x is kind of a basic parent function equation for your exponentials. Another common base number is e, all right? So you might also see something like y equals e to the x. E is a number just like pi. Hopefully you guys learned about e in your Algebra 2 classes last year, all right? But e is a special number. It's called Euler's number. It's approximately 2.72. It's a really important number in a lot of finance things and in calculus. It has a very special property in calculus that you guys will learn about next year when you get there. All right, we'll talk a little bit more about e later. Just know that it's another very common base number for exponential functions. And again, just like pi, it is a number and it has this approximate value of about 2.72. Okay, but what we're going to use for this one is just the 2 to the x because we know how to do these calculations a little bit better by hand. So that's what we're going to use as our function for this example. All right, so we just want to fill out this xy table. So if x is -2, we have 2 to the power of -2. Just as a reminder, negative exponents are your reciprocal. This is really 1 over 2 to the positive 2, which is 1/4. All right, so we can go ahead on our graph and we can plot that. So at -2, we have positive 1/4. I'm just going to go ahead and put a dot there on my grid. All right, when x is -1, you have 2 to the power of -1, which is just 1 over 2 to the positive 1, or 1 over 2. All right, so I'm going to go to -1. I'm going to plot that dot at 1/2. All right, 0, well, anything to the power of 0 is 1, so 2 to the power of 0 is 1. All right, so then we can just do 0, 1 as our next point on our grid. All right, moving onward, we have 2 to the first, which is just 2. So when x is 1, y is 2. All right, and then last but not least, we have 2 squared. 2 squared is 4. So 1, 2, 3, 4. There we go. Now, when you're doing the rest of your graph, you have to ask yourself, okay, well, if I plug in really big negative numbers, like -100, what is my graph going to cross through? What is the value of y going to be? Well, it's going to be a really small decimal number, right? 2 to the power of -100, all right, is a really, 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 really small decimal. All right, if you don't believe me, plug it in. It's super small, right? But that decimal number is still larger than 0. So what we have to recognize is that no matter what x value we plug in when we're in the negative direction, right, we're going to get really close to 0, but we're never going to be 0. And we're also never going to be a negative number. If you take a positive base and you raise it to an exponent, it is impossible to get a negative number unless there's other transformations that are happening. So we know that our value is always going to be greater than 0. So that means that it's going to kind of flatline at 0, and then it will kind of curve up. Now, because we are flatlining at 0, that means we have an asymptote right there at y equals 0. All right, we're going to get really close to 0, but it's impossible to actually get a value of 0. So that's an asymptote. Right, on the other side, we know that we are just going to keep growing. The larger x's we plug in, we're just going to keep getting bigger and bigger and bigger numbers for our y value. So we are increasing all the way on the right-hand side. So key features for a graph. All right, so looking at it, our domain, all x's are in play. It is all real numbers. All right, so just a reminder, we are going to use our interval notation. So we have parentheses, -infinity to +infinity, and parentheses. Remember, we use parentheses when we are not including something, and we cannot include infinity because it's fake. It's not real. All right, our range. All right, so again, if you look at our graph, we kind of are starting around 0, but we can't include it, and then we do continue to go up for forever. So our range, we would say, would be, I forgot this for the domain, x is in that interval, right? Y is in that interval from parentheses 0 to infinity. And again, we use parentheses around the 0 because we are not including 0. All right, next up, our asymptote. So we have a horizontal asymptote at y equals 0. All right, we talked about that on our graph. And then our y-intercept, where we cross the y-axis. This is an important point for our graph. All right, so right there at 0. All right, so this is that property that anything to the power of 0 is 1. All right, the reason why this is an important point for our graph, not only is it our y-intercept, it is also the point that regardless of your base number, every single exponential function with the same transformations will contain the same point. It's essentially the only point where our base number is completely irrelevant from the rest of the problem, which is why this is one of the points that we are going to use as we transform our graphs to figure out like where this point is going to go. All right, so it is a very important point for our function. So our y-intercept is that point, 0 for x, 1 for y. Okay. So those are our key features. The one thing I want to kind of go over, because we're thinking about transformations and how transformations are going to affect these different key features. These different key features. All right, essentially, the two things you're looking for are what's going to happen to your asymptote. What transformation is going to affect this? Well, remember, it's a horizontal line. If you shift a horizontal line left or right, it doesn't affect it because it's already going infinitely in the left and right directions regardless. So the shift left-right doesn't affect your asymptote. Also, stretching is not going to affect an asymptote. If you stretch it horizontally, again, nothing happens. It's already aligned. you can't stretch a line vertically. So again, that's not going to affect it. So there's only one transformation left, and that is your shift up and down. That is the only transformation that affects the asymptote of your exponential function. All right, so if you're trying to figure out where is it going to go, you're just looking at whatever your shift up or down is going to be, which, if you look at our transformation rules, your shift up or down, that's the d value. All right, so your asymptote is always going to be whatever y equals d is. The only transformation that affects that asymptote is your shift up and down, which is your d value. Now, for the y-intercept, this point plays on the fact that anything to the power of 0 is 1. So you can perform your transformation rules perfectly fine, super easy to do. Just remember, when you're doing transformations, you always want to dilate and reflect first, and then shift left or right from there. All right, and we'll go through doing transformation rules. But this is actually a really easy one to calculate algebraically. To find the x value for your y-intercept, you're just going to take whatever's in your exponent, equal it to 0, and solve for x. All right, because you're just figuring out what value would make your exponent equal 0, because that's what you're looking for. All right, so you just take your exponent, whatever's up there, you equal it to 0, you solve for x. Once you have an x value, it's easy to find a y value. If you know what x is, you just plug it in, and then it's going to tell you what y is for that specific x. All right, so then just plug the x value you get into the equation and simplify. Easy enough. All right, so you can use transformation rules 100%. I'm going to do transformation rules as I'm walking through our practice problem, but you can just do this algebraically, and I actually will show you both techniques. So we'll see how both kind of techniques work. Okay, so here we go. All right, it says, whoa. Determine the transformations that occurred, find the indicated values, and then sketch the function. All right, so I'm just going to go through left to right, look at my different transformations. Now, one thing to remember, changing a base number is not a transformation. It is just a changing of the base number. Remember, there is no standard base number for exponential functions. That base number can change. So if you look at ours right now, we have a base number of 3. That is not a transformation. 2 is not what it's supposed to be. It's just what we used for our previous example. So that 3 is not a transformation. All right, but everything else is. So the 2 out front, this is my a value, all right, which is going to be my vertical dilation. All right, so we have a stretch because it is greater than 1 by 2. Stretch by 2. You can say vertically dilate by 2. All right. I do actually want you to specify if it's vertical or horizontal. So instead of just stretch, I might say a vertical stretch. And if you want to be lazy like me, you can and just say VS for vertical stretch or VD for vertical dilation. I'm fine with that. I don't know why I didn't just get rid of the -2. All right, vertical stretch by 2. Cool. Next up, we are looking in the exponent. We have a -1. All right, this is going to be our shift left or right. And because it's a minus, that's telling me that it is going to the right. All right, so this is my shift to the right. All right, this is my C value in my equation. All right, so I am going to the right by 1. Last but not least, we have the -4. All right, this is my D value, and this is telling me that I'm going down. All right, so it's my shift left or right, and my shift up and down, and since it's a minus, I'm going down. So my last transformation is down 4. Okay. So those are my transformations. Now I'm going to find my different pieces. So for my asymptote, remember I told you guys above, the only thing that is affecting this asymptote is your shift up and down. All right, and it's really just going to be y equals whatever the d value is. So for our problem, our d is -4, so our asymptote is at y equals -4. So I go over to my graph, and I'm just going to plot that on the grid. So down 1, 2, 3, 4, And it's a horizontal y equals 4 line. Y equals -4. Beautiful. All right, now for my y-intercept, I'm going to first walk through how to do this with transformation rules, but I have a feeling most people are going to calculate this just manually using algebra because it's super fast. So normally your point is 1 up from your asymptote, right? So if we go up to the top right here, you notice at this point that we have right here, okay, it is 1 up from the asymptote. All right, and if you remember that, then you don't have to worry about shifting up and down because you're just going to move your asymptote and then go 1 above that. All right, so if there was no stretch or anything, I would be right here. However, I do have a vertical stretch by 2. So instead of stretching 1 away from the asymptote, I'm going to stretch 2 away from the asymptote. All right, so I'm going to be up 2. All right, so now I have performed my stretch. I'm not done yet, all right? I've just now stretched by 2 vertically, all right? I do still need to move right 1. So I'm going to take this point and I'm just going to move it to the right 1, and I'm going to erase the first one that I drew. All right, so I've shifted down, and I know that I just shifted down already, even though I didn't actually do it again because I moved my asymptote. All right, I just followed the asymptote. All right, so I moved the asymptote down by 4, which moved my point down by 4. I stretched it away from my asymptote by 2, and then I moved it to the right by 1. And now all you need to do is sketch the shape of the graph. You don't need to be precise. I don't need other points on this. This is all I need. All right, so this is my function right here. So my y-intercept has moved to be at +1, -2. All right, that was where that original point 0, 1 ended up. And that's the point that I want you guys to find. All right, now I told you guys I would show you how to do this algebraically, and I am going to right now. Okay, so if you didn't like doing transformation rules just then, what you need to do is you're going to take your full, whatever's in the exponent. So in this case, it's x minus 1. You're going to equal it to 0, and you're going to solve for x. X is 1. Right, that was really fast, right? So that's my x value for my new y-intercept point, and as you can see, I had a 1 when I did the transformation rules. Now I just have to find the y value. All I need to do is plug the 1 into the equation and see what I get for y. So it's 2 times 3 to the 1 minus 1 minus 4. 1 minus 1 is 0, so 3 to the power of 0 is just 1. So you end up with 2 minus 4. 2 minus 4 is -2. So I have my x, +1, I have my y, -2. That's my new y-intercept point. That's already what I had. Cool. All right, domain. Again, domain is never going to change. It's all real numbers. So we can just go ahead and say -infinity to +infinity. Wham, bam, thank you, ma'am, all done. All right, now we need to do the range. Right, looking at our graph, our y values are starting down at our asymptote, which is at -4, and it is going up to infinity. So we've got -4 to +infinity. That is our range. And that is it. All right, so I hope that was helpful for graphing these functions. All right, I do have another example that I'm going to fill in down below here, but you can just take a look at it here. I'll put it in the video. You guys can see. All right, so here is the next problem that I am going to graph. All right, but we're not going to walk through it. I'm just going to do the problem, and then I'm going to put the answer up here. So that's what I want you guys to do right now. So I want you to take a look at this. I want you to find your transformations, find your asymptote, find your y-intercept, find your domain, find your range, blah, 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 sketch the graph. All right, I'm going to pause the video. You guys should pause your recording right now and go work on the problem, and then when you think you have the answer, unpause and push play. Okay, so let's check and see if you got the right answer. All right, so this one thing I would recommend doing is doing what I did right up here and rewriting your problem so that you've pulled the negative, kind of GCF that out of your exponent at the top. so you can get a better idea of what's happening. The negative is indicating that you have a reflection, but you need to kind of factor it out so that you can see what your appropriate shift is. Remember, if this is confusing, think back to what we did when we were graphing trig functions. You always want to pull whatever number is kind of in front of your x out so that you can see your shift. So we have a vertical reflection, we have a vertical stretch by 3, we have a horizontal reflection, horizontal reflection. We're going to the right by 2, and we're going up 1. All right, our asymptote is going to be at y equals 1. Our y-intercept is 2, -2. You can do that with transformation rules. You can do that with the equation. I did it both. All right, your domain is never going to change. It's always all real numbers. Your range this time did kind of fluctuate because you reflected over your asymptote, so it's now -infinity to +1. But yeah, and then take a look at the graph and see how you did. So hopefully that wasn't too bad for you guys. That is graphing transformations. I know it was a bit lengthy, but we reviewed all those transformation rules at the beginning. Hopefully you were able to kind of skip through some of those. If not, maybe listen to me on faster speed. I don't know. But yeah, that was our video for graphing transformations. And I'll see you guys in the next one.